And all right, good afternoon, everybody. Today is Wednesday, March 22nd, and we are talking about the second half of our experience together in ES 2110 statics. So first of all, we have completed and I've graded everything for the first half of the semester. That includes 4 homework assignments, 1 quiz, and the midterm exams. So all of your grades have been entered and they should be available to you in Moodle, but your unofficial midterm grades are on the system when you look at your student records. So Moodle reports grades based on only the things that you've turned in. So if you haven't turned something in, I've tried to go back through and make sure that I put a 0 in so that your grade will calculate correctly, but it's not necessarily 100% infallible. And I see a different view of grades than you do, so it's a little confusing sometimes, but the place to look is really on the Northwest College system. The other part is that your midterm grade is a temporary grade. It will not show up on your transcript. So if you're not happy with your midterm grade, or if you've not submitted something, you still have time to submit it and it will be counted fully toward the final grade, which is your transcripted grade at the end of class. All right, so we're all done with the midterm exam and everybody took the exam. I was looking at the faces. Yes, everybody took the exam. So we are good to go. And we're starting our new after spring break schedule. The first most important thing is we're going to start with chapter 6. We're skipping chapter 5 till right before the end. And at the end, we'll do chapters 5 and 9, just because 5 and 9, the math tends to be more similar. So we'll do 6, 7, 8, and then we'll do 5 and 9. But my plan is to be in this classroom every Wednesday for the rest of the semester. Of course, as always, I'm still available to you at other times. If you need to set an appointment, you can use email and use Calendly, which is the scheduling program I used, or you can stop by my office. And this half of the semester, chances are quite good that I will actually be there. So that's it's all good. But I will be in this room unless I make a note on our schedule. I will be in this classroom on Wednesdays for the rest of the semester. All right, so that's sort of the big stuff. The thing about chapter 6, when we get started and it says Wednesday, November 2nd, please don't pay any attention to that. But did I get my dates updated or no? Okay, I got some of my dates updated. Okay, so our chapter 6 homework will be due it's just dated in a couple of days. That may be a little bit unrealistic, but basically we're going to use 2 techniques in chapter 6. And what we're starting to do in chapter 6 is an analysis of trusses, which I'll talk about specifically in just a moment. But this is an excellent lead-in for a class that you will take later called Mechanics of Materials. So this material is going to be the material that you're going to be starting with when you take Mechanics of Materials. It could be as early as the fall semester, or it could be later, depending on what your major is and where you go to school. But the material here has direct applicability to another class. So that becomes quite important. So the next thing I'm going to do is I'm going to talk a little bit about the content of chapter 6. If I'm able to pull up my PowerPoints, let's find out. Oh, there it is. Let's go ahead and open this, and we'll start working on getting ready toward the homework. There are several techniques for doing analysis of structures, but we are only going to focus on 2 of them. And my PowerPoints don't want to open up for me, so I might have to freehand it, which I'm sorry if that happens, because my freehand is not as good as it should be, but I can do it just the same. Let's try and see if we can open it up this way. Yeah. All right. So maybe not. Maybe we're not going to get to. All right. So I'll do a combination of freehand and And what's going on if my PowerPoints come up, then lucky for us. But anyway, so basically, let's talk about what we're doing. When we talk about any sort of a structure, let's see if I can turn this to a different view so that you can, full screen or the other person. Just want to see him over and over again. There we go. All right, let's do that. Now I'm going to go ahead and share the screen so that Grant can see us. There we go. All right. So no. There we go. Yay, we got the PowerPoints. All right. So basically what happens with, and you may not even really be aware of it right now, but when we have done analysis so far, we've done summation forces and summation moments, we have assumed that everything that we place upon a structure is going to be borne by the structure. In other words, it's not going to deform and it's not going to break. We just say, this is the load, how does it distribute? But we also know in real life that that's not 100% true, right? Loads distribute, but if the members are not strong enough to bear those particular loads, that a deformation or a rupture will occur. So what we're talking about in chapter 6 is actually an introduction to that. If you have some sort of a brace like this, you have a weight hanging on the end of a beam, and the beam is supported here, okay? And then we've got this support here. What ends up happening is the load from this weight is distributed among those structural members in order to bear the load in a particular way. Now, previously, we could have done something like this, and we could have said we have a weight here, and we could have eliminated this structure, for example. I mean, there's nothing that precluded us from doing that. But if you look at that structure, if we eliminated the structural member BE, what would actually happen, do you think? In other words, if we eliminate this cross-structural support, and we just have this borne right here, okay? All of the force from the weight is being borne on this fastener, point C, and it's quite likely that if the weight is heavy enough, that CF would actually collapse and fold into the upright support. We have no way of knowing that without doing the math. However, when we put in a cross-structural support like this, the reason is that we want to have the load borne in a different way. So in a little bit, we're going to talk a little bit about bridges and some roof trusses and so forth. But basically, if you have a structure like this, everything is going to bear loads based upon the structural integrity of the structural members and the geometry of the load-bearing members. So what happens here, we are doing a three-body diagram of not just the upright structure, but the entirety of the three-beam structure. The upright AD, the horizontal CF, and then the cross-structural member BE. So we take that as a whole piece, and then we say, what's happening to that structure? Well, we have a tension being pulled on from this wire, from this guy wire. We have a weight pulling down. And as you see here at point A, it's like a hinge, which is a silly kind of a support to put there, but there it is just the same. So we can have a force that could be borne in both the X and the Y direction. Now, we may also be interested in what's going on in the structural member BE, or what's just happening to the vertical member AD. And so it's equally valid to break down just the vertical member AD, and then what happens is whatever is attached to it, CF, for example, just exhibits itself in a horizontal and a vertical force at the fastener, and the same at B. We have some sort of an angle force that we could also break down into a horizontal and a vertical component at that point. So it's equally valid to look at any part of the structure, the whole structure, or any part of the structure, and consider everything that's touching that structure or that structural member as just acting upon that structure. Because in order for this to maintain static equilibrium, in other words, in order for the summation of forces in the X and Y direction, later in the Z direction as well, and the moments on everything to be zero, it has to be zero everywhere, whether you just look at one structural member, or you look at part of the structure, or you look at the entire structure. Everything has to be zero, or it falls down, or collapses, or bends in on itself, none of which we're interested in have happening. Yes?
When you're referring to summation force, you mean net forces?
Yes, exactly. So just like when we've done in the past, summation forces in the X direction equals zero, right? Yeah, that still has to be zero, whether we're looking at the whole structure, just one piece of the structure, or some composite piece that's part of the structure. So, yeah. So very good question. All right. So the next thing that we look at is a very important type of a structural member, which is called a truss. A truss is built on a triangle. And the reason, if you think about it, a lot of things that support a great deal of weight, such as bridges and roof trusses, are built on the structure of a triangle. And it's because triangles don't tend to collapse on themselves. If you push on them, they tend to maintain structural integrity. Now, it's not a for certain thing. It's just more likely that if it were built on some other type of a structure. But if you look at this type of a truss, for example, you can see that you can think of it as one large external triangle, or you can think of it as two smaller internal triangles. But in any case, everything has to maintain that structural integrity, and everything has to maintain that summation of net forces equal to zero, and moments as well. Now, the other thing is, this isn't really brought out in this class. You'll talk about more about this when you take mechanics of materials, but certain types of internal forces tend to be born at connections. And so, for example, this truss is drawn with a stress place that is heavily bolted or riveted at those connections, because that's really where everything concentrates, certain kinds of stresses concentrate. So we'll talk about that more later when things go on. But once again, if you look at the entire truss, or if you look at part of the truss, everything has to sum to zero. Now, the other thing is, every load or every force that is born in a structural member, may seem like a silly point, but it's still true. The direction of the force is going to be exactly the same as the direction of the structural member. In other words, if the structural member is vertical, C to D here, C to D will only bear vertical forces. A to B will only bear horizontal forces, and something at an angle C to B, the force is always going to be borne along the structural member. So this is a diagram of maybe A to C, and the two possibilities of what can occur. The first shows that structural member in tension because it's being pulled apart, right? The other shows it in compression because it's being pushed together. In a truss, there's really only three choices. Those structural members are going to be in tension, they're going to be in compression, or they're going to be neutral. If they're neutral, they're really not needed. But in certain cases, they're not needed sometimes, and then they're needed other times. So, but everything should have a purpose. And so ultimately, although sometimes they calculate to be zero, in order for them to be effective, they should always bear a load or be able to bear a load that may happen within the loading conditions of that particular structural member. So as it says here, this is a three-dimensional truss. Members of a truss are slender and are not capable of supporting large lateral loads. Load must be applied at the joints. Okay, so that's just the way the trusses work. This next is a diagram of different types of trusses. Pratt, Howe, and Fink are typical roof trusses. Bridge trusses, Pratt's also fall into that form, and it's just based on the geometry. Howe, Warren, Baltimore, K's, and then there's some other types of trusses and general trusses. One thing you can notice about roof trusses, they tend to be pointy, just because that's how roofs are constructed. Bridge trusses tend to be flat on the top or to have a different type of a geometry. But in all cases, they are sums of triangles. You can see that they're just like the Fink truss starts with a large triangle in the middle, and then three-sided triangles are added to it to build up structural strength. Every one of these is bearing a load, and it's comprised of members, which are the structural members, whatever those are, and the joints, which are where they come together. All right, so here's just some ideas about simple trusses. Once again, a simple truss, the kind that we're interested in this class are called rigid trusses because they do not collapse with the application of a load. So the diagram here of this quadrilateral ABCD is not a truss. If you look at it, if it's supporting its own weight at AD and you apply a compressive load at B, this is going to collapse. C is going to spread out a little bit. B is going to depress downward and to the right. So this is not a rigid truss. ABC here, if you push on B, A and C, AB and A and BC go into compression, but it does not collapse. So anything that's built on I shouldn't say anything. A rigid truss built on a triangle has that effect. Okay, so it gives you a little bit about the geometry of a rigid truss. Okay, so there are two different methods that we're going to talk about, the method of joints and the method of sections. And once again, both of these methods have point of applicability. Generally speaking, method of joints is mathematically easier, but using method of sections, you can often jump especially to an internal member and determine what's going on in that internal member much more quickly. So with method of joints, you may have to spend 5 or 6 layers of calculation, and in the appropriate situation, method of section will get you there in 1 or maybe 2. Okay, but basically, so we start talking about the method of joints first. And in the method of joints, what we do is we look at our truss, and first we do a free body diagram. We decide what the external and the reactive loads are going to be on that truss. And then what we're really trying to determine is what is going on in each structural member. And when I say what's going on, I mean, what is the magnitude of the load? We already know it's directed along the structural member itself. What's the magnitude of the load? And is that load a tensile load? In other words, is it in tension or is it in compression? Okay. And so this is just a very complicated type of an analysis, but a space truss is just something that's not two-dimensional. We're not doing any space trusses. We're just doing two-dimensional trusses in this particular class. Later on, you'll get into space trusses, but for now, we're going to stick with 2. All right, so how do you do it? This is a typical truss, and the first thing that we're going to do is to decide how to solve this. And when you say solve a truss, it means what is the structural load? What is the load in AB? And is it in tension or compression? What is the load in BC? Is it in tension, compression, and so forth? So you chase all of the structural members of the truss, or if they identify 1 or 2 that they want to get the load in, that's what you do. But it's always focused on what the load is in a structural member and whether that load is in tension or compression. Okay, so the first thing you do, we start out with good statics. You do a free body diagram. So you look at the whole truss and you decide what's going on the outside. This particular truss, we have 2 applied loads, and then we have a reactive load here at E and a reactive load here at C. So in other words, C and E are going to have loads based upon the fact that it's being pushed on. You can probably see that E is probably going to have a vertical load pointing straight up because these are vertical loads pointing straight down. So it kind of makes sense that E is going to be pushed down and E is going to push back up on the truss. But you may not know that all the time. C has the capability of bearing both a Y directional force and an X directional force. And E, if this is like your author's code for a structural member, when you see a roller support like this, that means that it slides freely in this direction. So that means it only bears a load perpendicular. Okay, this is a fixed support, so it will it could bear both an X and a Y load. I don't know that it will, but it can. Okay, so that's just sort of a point. This is their little code for here. We have an E sub Y, but we do not have an E sub X. Okay, so the first thing we do is to determine what those loads are. Draw a free body diagram, which is going to look like this, right? So we have those external loads, we have the reactions at C, we have a single reaction at E, and then we do our summation forces X, summation forces Y, and summation moments, just like we've been doing since chapter 2. So we start with that and we determine what those are. We find that C sub X is equal to 0, which we'll talk about in a minute. And we find C sub Y, and we find the reactive force at E, which I would probably just go ahead and call it E sub Y, just to be clear. But that's my preference. You don't have to, if there's no E sub X, you don't have to subscript it, but I think it's more clear if you do. So, but you won't be counted off if you're able to keep that in your head all the time. Now, if you look at this particular truss, and you look at the fact that it's attached to the wall here at C, and you think about the fact that there could be a C sub X and a C sub Y force. Well, since E cannot bear an X directional force, and these two forces are both Y directional, it's not possible that there's an X directional force here. The reason is there's nothing to oppose it. There's no way to reach static equilibrium with a single X directional force. So unless there was something added to it, like if you put a X directional force here, C could respond with an X directional force, but with this configuration, it's not possible. So you can kind of see that. The other thing I wanted to show you is if you don't know the direction of the forces, just like when we've done this before with frames or whatever, if you don't know the direction, it's best, in my opinion, to assume that they are all positive. So in other words, C sub Y and E point upward, C sub X points to the right. So in other words, I don't really try to give a lot of thought to whether it's positive or negative. I just assume them to be positive. The reason for that is, if you look at this equation, for example, you would find that C sub Y turns out to be negative, okay? And the reason that that becomes important is because if you called C sub Y negative in your three-body diagram, and it's negative in your math, that actually means it's a negative negative, which is a positive. So if you always assume unknowns to be positive, the direction in your math will be the actual direction of the force. So it's just sort of a bookkeeping tool that is somewhat effective. Okay, so continuing with this, now they use triangles, which is fine. The method of joints says this very simple proposition, which is the forces coming in to every joint must sum F sub X equals 0 and F sub Y equals 0. Okay, so in other words, our conversation about the static equilibrium extends itself to those points of connection. So anytime that you have a joint and you look at the forces coming into it, whatever their directions are, when you break them down into X and Y components, everything coming into this joint has to sum to 0 in the X direction and the Y direction, or any other two perpendicular vector directions. But that is key to how we use the method of joints. Now, I personally, once again, I really avoid using a strict trigonometric method like this. The reason being that if you do summation forces X and Y and you break everything into components instead, that carries better into 3 dimensions, even though we're not going to do 3-dimensional stuff here in this class. It's just a little bit more generalizable if you learn that method pretty much exclusively. But if we wanted to know, for example, let's see, okay, what I have on the board here. If I wanted to know what's going on here at joint C, how can I analyze joint C? Okay, I'm going to just draw this out on this paper, and then I'm going to put this to you I'm going to draw it out here. I'll show it to you here, and then I'll show it to you in a little bit here. So, all right. So if you take a look at joint C, which is right here, in this particular problem, there's C sub Y acting vertically on it one way or the other, C sub X, which is equal to 0, right? We already determined that. Then there's a horizontal force here and a force here. In other words, the structural members that go into the joint can at that point be viewed as forces. Okay, so you're looking at what the force is being borne in that structural member going into the joint. So let me get my things here. All right, so here at point C, this would be B sub C. And this would be E sub C. All right, I'm going to get a little bit of direction here too. The distance from E to C is 6 feet in the horizontal direction. And the distance from E to C in the Y direction is 8 feet. Okay, so this is the picture that I have drawn so far. All right, now the next question is, I know that E sub C and B sub C have to be directed along those structural members, but what is the direction? Well, here's the way that this works. If you look at this, this is vertically upward, right? This does not have a vertical component. So in order to maintain a force equilibrium in the Y direction, if this is upward, this is going to have to be downward, right? Because that's the only other, that's the only way we can counteract a horizontal or a vertical force that's upward. Let me take a look at this for a second. Just wanted to see what I came up with for C sub Y up here. Yeah, so here, so this is actually C sub Y is downward. I found from my statics of the whole product of the whole truss, and C sub Y is 7,000 pounds down. Okay. Let me come back over here to my drawing. Okay, so if this is going downward, 7,000, this one is going to have to be going upward, right? And further, the vertical component of E sub C is going to have to be 7,000 pounds. Now I'm going to have to work that out mathematically. But if this is going down, this has to be going up, which also means that it's going to the right, which means that this one has to be going to the left. So in other words, I'm breaking down my Y and my X and making sure that everything's going to be able to cancel to 0, right? All right, so let's see what that looks like. We'll say coming into joint C, summation of forces in the Y direction has to equal 0. And the summation of forces in the X direction has to equal 0. What do I have going on in the Y direction? Well, I have minus 7,000 pounds, and then I have plus E sub C in the Y direction. Those are the only two vertical forces I have, so they have to add to 0. In the X direction, I have negative B sub C, the whole thing, because it's purely horizontal. And then I'm going to have plus E sub C in the X direction. And that's the only two horizontal forces I have. That has to equal 0 as well. Okay, now right now it doesn't necessarily look like I have enough data to solve this, but let's take a look at this triangle E sub C. Okay, this is EC, this is 8 feet, this is 6 feet. Okay, so if this is E sub C, I can find out what this angle is. So I can say theta, I have the opposite and the adjacent, which is the tangent function. So it's the inverse tangent of 8/6. And so that theta is the arctangent or the inverse tangent of 8 divided by 6. And that gives me an angle of 53.13 degrees. Okay, so when I know that this angle is 53 degrees, what do I know about my Y direction? Well, negative 7,000. I need more paper here. Let me get this off of here. Negative 7,000 pounds plus E sub C in the Y direction, which is going to be E sub C times the sine of 53.13 degrees equals 0. Okay, now that's an equation I can solve because it's one equation, one unknown. So I have E sub C is going to equal 7,000 divided by the sine of 53.13 degrees. And that means that E sub C is equal to sine answer 0.8, which I already knew. And then 1 over that number. Multiply that by 7,000. All right, so E sub C turns out to be 8,750 pounds. All right, now we need to find out what B sub C is. But we can say then that E sub C in the X direction, which going back to my triangle, is going to be E sub C times this time the cosine of 53.13 degrees is going to be minus B sub C equals 0. So that's equal B sub C. So I know the value of E sub C, 8,750 pounds, times the cosine of 53.13 degrees equals B sub C. So cosine 53.13 equals 0.6, which I knew from this diagram, times 8,750 pounds equals 5,250 pounds equals B sub C. All right. So now I have the magnitude of the forces being borne in the two structural members coming into joint C. The only question now is, are they in tension or are they in compression? Okay, you can't really tell from whether the arrows are positive or negative in the X and Y sense. What you need to do is to think about whether that is pulling on the joint or pushing on the joint. If it's pulling on the joint, it's in tension. So if you think about B sub C, it's pulling on the joint. And like E sub C, it's pushing on the joint, right? So that means B sub C is in tension and E sub C is in compression. Okay, so when you write your answers to this, you would just say B sub C equals 5,250 pounds tension and E sub C equals 8,750 pounds in compression. And that's the format for the answers of problems like this. Okay. That's kind of drinking water out of a fire hose. That's a lot of information to digest in one day. But having said that, do you guys have any questions about that? Okay, so then the next thing one would do is you can chase that back. Now you know, for example, what B sub C is, okay? And we know that the magnitude of B sub C is 5,250. We know that it's pulling on the joint. So the only weird factor is that when we get over to B, it's no longer pushing over to the left. It's still pulling on the joint. So in other words, it switches absolute direction. So in other words, at B, did I draw that? Oh, here we go. Let me unshare my screen. At B, because B sub C is pulling on the joint, if we then analyze joint B, it would be pulling on the joint. So it would look like this. It still has the same magnitude, but it has an opposite direction. Same thing here with EC. We know it's pushing on the joint. So when we get down here to E, it would be pushing on joint E as well. Okay. So in that manner, you can chase all the way through that truss. Now you know what BC and EC are. So you could analyze joint at E. So you could get this and this. And once you have this, you'll have this and this. You can get this and this because you can only have two unknowns going into a joint, right? Because you only have summation forces X, summation forces Y. You can't do moments because anytime that you took a moment, it would all be zero because you're taking about a particular point. So all the moments going into a joint are inherently equal to zero. So you just have two equations that you can work with, summation forces X and summation forces Y. All right, so do you guys have any questions about this material so far? All right, well, I'm not going to get into method of sections today because this is a lot. What I'd like you to do is to give this a go and see how it goes out for you. Then we'll talk about sections of sections of methods. I've talked about methods of sections. I have recorded videos that will build on this lecture, but I'll also be available if you want to meet on Friday or Monday. Just send me a note and let me know. Or if you want to meet individually, we can talk about it, or else I'll talk about it again next Monday. Even though we're passing up the due date, still okay. You can get this stuff done on the method of joints. You'll have a good start. All right. All right. Well, that is it today. Thank you very much for your attention. And